Good day to you, ladies and gentlemen, and welcome to the second lecture of the second module in the Jabrah Statistical Machine Learning series. So, what we've covered so far was just a basic introduction on what we're going to be covering and just a few loose terms that we introduced. So, we haven't actually gone to the core of anything yet. But one thing I just want to say is that you don't have to worry about the module 1 on reinforcement learning. We're still going to add more lectures within that module. So this module is running in parallel with the other module. So having said that, let's actually get started here. So one thing you might ask yourself is, why are we talking about polynomial curve fitting, right? What does this actually have to do with statistics and machine learning and so on, right? You might actually have this question. And the thing is that this technique actually is going to help us solve a certain class of supervised learning problem that we call linear regression, right? And this is actually where we're going to get started. It's quite simple and it's easy to get into. So it's a good place to start, I believe. Therefore, we're going to be talking about linear regression, which is a supervised learning problem. I hope you remember what supervised learning is from the previous lecture. If you don't, just go back to it and you'll know. Having said that, so what are we going to do, right? We're solving for a supervised learning problem, linear regression. Let's actually start with an example. I think that will make things much more clear. So we're going to start with an example, right? So you're given a training set. A training set, if you remember from the previous lecture, we introduced the concept of what a training set is. And this is X, which is essentially X1, X2, all the way up to Xn. And then we have T, which is the target, which is T1, T2, up to Tn. So in case it wasn't clear what a training set was last time, this is kind of like in the beginning, this is information we have. In the previous lecture, we say that this can be an image, right? X1, X2, Xn, they can all be images, and T1, T2 can be the corresponding categories of those images. Is it a number? Is it a car? Is it whatever? Like it can be anything. So this is how we had defined what our training set is. This is how we had defined how it is. So this are what we call our features, right? And these are our targets. So X is representing our features and our targets. So later on, we'll when we're actually kind of trying to create our test set, right? So let me use a different color. When we're trying to make our predictions, so this is let me make this clear. This is X train, right? And then we might have another one which we consider to be X test, which will be X1, X2, whatever, up to some point. And then we're going to try to predict our targets. So we don't know what this is. This is what we're trying to predict. So based on this, you can go like, okay, based on this information, we're going to try to form some kind of thing we call a model. You don't have to know what that is yet. We're going to discuss that later on. We're going to form something called a model that learns from this data such that when we feed this new information, it can actually make predictions based on this, right? So what can X be? So in the previous we said we're talking about it can be something like image, but it can also be something simple such as, let's say someone gives you a problem. Can you predict the price of a house if I give you just the size of it, right? So he gives you a bunch of different house sizes and the corresponding prices, and then he asks you to devise a model such that if you input a new size, it outputs what the price of that house possibly is. This is kind of like another problem you can have. So X is just representing features that the information that we have, and T is representing what we want to predict. So let me make that more clear. So X here is the information we have, and T, our target, is representing what we want to predict. So that's kind of like the relationship here that we have. So anytime that we want to predict a continuous variable, right? So predicting continuous, sorry, yeah, continuous variables, what happens? So if we're trying to predict continuous variables, we're solving for a regression problem. The class of problems for this is called a regression problem because we're predicting continuous variables. When we're predicting more like categorical variables, like is it class A, class B, class whatever, this is what we call a classification problem. So here, we are actually going to be talking about predicting continuous variables, which is the regression problem first. So we will deal with these problems later on. So for this lecture, we're going to just be focusing on regression. Having said that, back to our example. I guess I skipped a bunch of it to introduce some information. So we're given a training set, right? Someone gives you a training set. And then you go like, okay, let me plot that training set, right? So the training set consists of a bunch of numbers, x1, x2, blah blah blah, and a bunch of targets, t1, t2, blah blah blah, right? I'm not going to actually go into actual numbers here, but so let's say you decide to plot these things, right? You're like, oh, let me use a darker color, I suppose, might be better. So you decide to plot right. You decide to plot what you call this x versus t. That's essentially what you're plotting. So this is your x here, and this is your t, right? So based on this, maybe I should clear things up a bit. Let's see. So based on this, the goal is actually to make some kind of prediction, right? So is there a, let me try to remove this point here. Okay, much better. So based on this, we are trying to make predictions, right? As to if someone says, if I give you a new x, right, I want some model that will predict what the corresponding t is, right? So basically, if you're given the x can be, if you're given an x at this point here, x prime, what's the corresponding t for that? How can you know? Or if you're given x double prime, yeah, so this is what you're trying to given, and then you are trying to understand what's the corresponding value of t. So this can be, if I give you this size of the house, what's the corresponding price? This is kind of the questions that someone might ask you. So the application of regression problems is actually quite vast, right? So it's not only for predicting house prices or whatever, but anything that has a continuous variable, you might actually discover that maybe applying a regression model might actually work. We'll talk about this in more detail later on. But right now, I just want you to understand the concept, to gain the conceptual understanding behind this. So how would you solve this? So what I would try to do is probably go like, what if I just draw a line here? So a nice line there, like that. Okay, you draw a nice line like this, and someone asks you, so what's the price of this? I just go to this part, So for this x, what's the corresponding t? You just come here, right? You just go up to this point and go like, huh. So for this, the corresponding t is this one, t prime. Or for this, the corresponding, let me extend this more. No, sorry. So it's like that, whatever. For this, the corresponding t is here, whatever it is, right? T double prime. So you can make this kind of predictions once you have this blue line here. So that's essentially what regression is, right? Basically, you're just given a bunch of points, data points. And then based on that, you're trying to predict the perfect line, the perfect fit here. Because based on this, you can now say, if someone gives me some point here, x prime, I can easily predict what the corresponding t prime is. That's the essence of regression. This is it. Trying to fit in the best line possible for our data set. And that's why we call this polynomial curve fitting, because that's essentially what we're doing. We're trying to fit in the best curve for the data that we have. So one thing you might ask yourself is, okay, what is it here that we're doing? We're trying to fit the best line so that we can use this line to make predictions. So you can actually think of this as our model in a sense, right? You can actually think of it in that way. Like this is actually our model because we're going to use this line to make those predictions anyway, right? So it takes x as input and tries to predict what t is. That's what it is. So it's quite simple to understand conceptually, but the one thing you might start thinking to yourself is, how do I actually compute this line, right? And that's actually a good question. We're gonna get into the details of how we actually compute this line, but for now I'm just gonna give you a high-level understanding on how to do it, right? So first thing first, you might think to yourself, okay, let me use a fresh page to illustrate this point. So first of all, let's say again, we're given a simple data set like that, right? And we have our points. This is our data set, right? So, how am I supposed to know, like, this line should be, what's the polynomial factor that I should actually apply to this line? Because it can be anything, right? This looks kind of like some representation of some sine wave or whatever. So where do you actually start, right? Trying to figure out the equation of the line that fits this, right? And up to what factor does it reach? This is kind of one class of problems that's actually known as model selection. But let me actually not get into that yet. Let me just show you a simple example. So the line, one option for a line could be, okay, let me just fit this line. What's the equation of this line? This line can be seen as y is equals to, let's say, w0 plus w1x, right? Where this is x and this is y. I'm using y instead of t now, so you can just interchange those. So this is a simple equation of the line. W0 plus y is equals to w0 plus w1x. That's how you represent the equation of a line, right? But what's the problem with this? This line is not sufficient to represent this, right? As you can see, this line, because it only has up to a polynomial factor of 1. There are no squared terms, there are no cubed terms, and so on. So it's not sufficient to model this problem by just using this equation. So this is not sufficient. Why? Because this is the best you can do, right? There's no way you can actually have any curves coming here because this is the equation of a straight line, right? This is the equation of a straight line. So this is actually the best we can do with this information. So up to how many up to what polynomial factor should we go? Because you might think of this as, okay, we can say y is equals to w0 plus w1x plus w2x squared plus w3x cubed, and so on up to w, right? Let's say x to the power m whatever. This is one way that we can think of this, right? This is how we actually represent our y, right? Like by this strange equation up to some polynomial factor of m. And then maybe in that case, the equation can now be complicated enough to model this strange data set that we have here, right? So the problem becomes this. If your polynomial factors are too large, you will encounter a problem called overfitting, which I'll describe later. If they're too small, you encounter the problem that we have here called underfitting, which again I'm going to explain later. But for now, you just need to think about it in this way. We need to select some m, right? A sufficient value of m such that we can model this perfectly. This is what we're trying to do. So how do we decide on what that m value is? So let's rewrite this again. So we said y, which is dependent on x, and it's a function of x and w, is equals to w0 plus w1x plus w2x squared plus up to wm xm, right? This is how we describe it, which is just the same way as saying summation from I is equals to 0 up to m, right, of wi x to the power I, right? This is the same information here that we wrote down there. So this is essentially the same information. So we need to see, like, how do we select this m? That's the first question you might have. Another question you might have is, how do I know the correct values for w? This is the equation of a line. We just say w0 plus w1x, but what is w0 and what is w1? What is w2? How do you compute these values? That's another problem. So let's go back to this thing, right? Let's go back to our graph. I'm going to draw it again for clarity. We're going to go back to our graph here with our nice data set that looks like this. And then we're going to ask ourselves, like, how do we want, let's say it's you're given this, right? How would you solve this problem, right? You want to draw a line such that the distance between that line and the corresponding points is the minimum. So you want to make sure that the distance between here and here, let's say we had some other points here, some other points there, right? We want to just make sure that the distance between each and every point, right, and the actual line is minimized, right? So this is why we want to kind of like, we're solving a minimization problem, right? This is an optimization problem in a way. So exactly what are we trying to do here? Well, if you think about it, this is actually, this line is representing y, x, comma w, right? This is what this line is. It's y, x, comma w. So this is our prediction, right? This is our prediction. And then we say that since this is a data set that we are given from the beginning, we will say that we're given this data set. Okay, let me use it here. So this data set actually, okay, let me use the same color as red. So this was just x1, t1, x2, t2, up to xn and tn. This is the data set that we have here. That's what this data set is representing, x and the corresponding t's, right? So now we want to make a model such that if you give it an x, it will try to find an x that's a t corresponding t value that is as close to the actual t value as possible. So what do I mean by that? So we have three classes of problems here. So we've got, like I said, we have x1, right? And then we have t1. So we know what x1 is because it's here. This is x1 t1, let's say. This is x1 t1. This is, say, x5 t5. This is xn tn, right? We know what t1 is. x2 t2 x5 t5 and also up to xn tn. So we know the values of these things, right? But then we are going to try to predict ourselves. Let me use blue. So we're going to create our own y of x1 up to y of xn. But y should not just be a function of x1 and xn, actually. It should be x1 comma w up to y xn comma w. So this is what we have. So what is this y representing? So we know that we want t minus t1 and y of x1 comma w to be as small as possible, right? This is kind of what we're minimizing. So essentially we can think of this as t1 prime, t2 hat rather, and tn hat, where t1 where tx hat, so where tx hat is equals to y x, should use a different subscript here. Let me use whatever, like an O here, whatever this is, comma w. This is essentially what we're saying, right? So this is our prediction, and this is the actual, and we want to minimize them. We want them to be as small as possible. So in other words, we are saying that we want the value of t, let me write it this way on a new page. So we want tn minus y xn comma w to be as small as possible across all values of n. So for all values of n, where n is the data points, we want the difference between the target and the predicted. So this is actually what we call the target, and then this is our prediction. We want them to be as small as possible, the difference between our target and our prediction. How do we ensure that these two things are as small as possible? This is the question that we have, right? Well, it's not actually that difficult. We just solve a minimization problem, right? So we consider the difference between tn and yn. So the difference between target minus prediction. This is what we call the error, right? This is our error. Because if they differ by some value, that means we're off by that value. So that's what we consider to be the error. So we want to minimize this error across all possible terms. So given some value of w, so we're now representing this, we're going to say, we're going to look at y xn comma w minus tn. So we can take the absolute value or we can square it, because we always want this error to be positive. If it's negative, it's going to cause some problems, and try to convince yourself why that is. But we're going to say our prediction, and this is our target, right? And we're going to say we're going to square this, right? And then we're going to say the summation from I is equals to 1 up to n, right? And we'll have another term here for convenience, but I'm not going to put it there. So essentially, yeah, actually, let me just put it there. So don't worry about what this 1/2 is. Just forget it for now. It's just later on, I'll explain what it is. But what you're supposed to get is that we're trying to minimize E of W, right? This is what we're trying to minimize, because this is actually representing the summation from I equals to 1 to n of the error here. So this is the error, right? This minus this. So we're trying to minimize this error between this. So how do we actually go about minimizing this error? You don't have to worry about that right now. We'll discuss this in a future video. Just for now, you just need to be able to understand two things here. From if there's anything you're going to understand from this lecture, let it be two things. The first one is the idea of model selection, right? That we're talking about, like up to where should we choose our M so that it represents this appropriately. And the other problem is that of, okay, assume that we know how to choose this M, right? We know what this M is. So we know what our y, x, comma, w is. How do we actually find the values of w, right? How do we find those weight values that we're going to use to make our predictions? So basically we find them by minimizing this equation, right? By minimizing the error, the total error, the sum of errors. So this is actually, it actually has a special name. So this is, it's called SSE, sum of squared errors, right? So you can take the sum of squared errors, you can take the sum of the absolute values, and so on. So there are different ways that you can actually compute this. Some of them have their own advantages to others. It's something you should just be aware of. So essentially, how do you actually, that's one thing, how do you minimize this error to begin with? I say don't concern yourself with it, and that's fine, we'll discuss it in detail later on. But one thing is, if you're familiar with derivatives, if you're solving a derivative, where is it minimum? Like, what's the minimum point of a function? Like, if you think about derivatives. So the minimum point is where the derivative of a function equals 0. So one thing you can think of is taking the derivative of this function, making it equal to 0, and then solving for that. And again, we're not going to go through that here. We're going to go through it maybe in a future video. Just for now, we're just trying to make sure that you get a high-level concept, like a high-level overview. So having said that, let's actually get our hands a little bit dirty and actually solve this, because right now I just talked about this example from a conceptual point. If you're still confused, it's okay. I'm going to go through a programming example of what we're doing here. So let's start here. The first thing we've got here is, so I wrote some utility functions. So right now you can ignore all of these functions that I have here. So you can ignore them. You don't need to understand what's happening. You will in a later video when we actually go through all these topics about data generalization, and solving this kind of problems. But right now I just want you to get a general idea, right? So first of all, we have a data set where we say x is our features and y is our target, right? So let us actually plot this data set first. So plt dot scatter x comma y, and let's actually show what it looks like. plt.show. Okay, so I'm going to run this. So this is what our data set looks like, where this is our x. I should have put the title there, but you should get the idea. This is our x and this is our y, our predicted y. So we are trying to find the best line, right, for this. So the first thing we discussed, right, was, okay, so you have this graph. I'm going to just, so the first function we have here is generate dataset, just generating our x and y. The next thing is choosing the right value of m, right? Do you remember what that was? Let's go back to where we were. So the first problem we were solving in the beginning, we said we want to find here. So the equation of the line that's going to be fitting this is y by w0 by w1 by w2 by w3 up to wm. And then we say that how do we choose m, right? So for now, let's actually try to just choose m is equals to 1, right? M is equals to 1 here is going to give us just w0 plus w1x, right? So this will give us the equation. Let me use a new page here to make things much clearer. Let me draw this again. So we have that. And so on. And first of all, we're going to choose m is equals to 1. And m is equals to 1 is going to give us the equation y is equals to mx plus, w0 plus w1x up to x to the power 1, right? This is what m is equals to 1 is going to give us. We're going to also try m is equals to 3, which should give us the equation. So this is m is equal to 3, and m is equals to 3. This should give us the equation y is equals to w0 plus w1x plus w2x squared plus w3x cubed, right? So that's what m is equals to 3 will give us. And then we'll also try, say m is equals to 7. And this should give us y is equals to w0 plus w1x plus w2x squared all the way up to w7x to the power 7, right? This is what these equations are. So this is model 1. Model 2. Let me make this, instead of 7, let me make this be, let's have it be 11 or something, so that it's really an overkill or something. So up to w11 x to the power 11. So, and this is our model 3. So we have these 3 different models that we're going to try to fit into here. What we'll discover is that model 1 is actually going to look like this. It can only do up to a straight line, right? It should be. And let's actually go to an example to make sure of that. So the first model, which we'll call x1, which is our model 1. So let's get optimal weights for x1. Our first model here. Actually, let me just leave it like this. So here you got expand polynomial. This is just giving us the model up to model 1. So you don't need to understand the how it's working in the background right now. We're going to go through that later. But using this, we're going to compute the optimal weights. So what are the optimal weights actually? We're going to do this whole minimization where we try to reduce the errors between the target and the prediction and stuff like that. Again, you don't need to actually understand how it is, but just imagine that this function gives us the optimal W for our given X, for our given model, which is M1, model 1, model 2, or model 3. That's the idea. So let's actually plot it. So we're going to plot. We're going to plot X versus the prediction, which should be MP dot product um, between, so this should be a dot product between this x underscore and the w. So this is x. This should give us our prediction. Why? Because again, if we come back here, how do we actually compute the prediction? Where is it? This is, okay, let me go back to this example. This, we can actually write this as a dot product, like in matrix format, as to be x transpose y is equals, sorry, x transpose w is equals to y, right? Because this is what the dot product essentially is, like x trans. So if we represent our x as a matrix, our w as a matrix, we can just compute the transpose and stuff like that. And this is essentially what's going to give us. So let's plot it in a different color. Let's make it, let's, there you go. We'll plot it in red and see how it looks like here. So as you can see, this is the best it can do with this model, right? So this is the output of model 1. What do we see here? It's what we call underfitting. The model itself is not complex enough to represent the data set that it has. So that's the first case we have here. So model 1 is underfitting. Is underfitting. So which means the model itself is not complex enough to represent the data set. Right, that's what we consider to be underfitting. We need to make it more complicated. And in this case, the only way we've learned on how to make a model more complex right now is by increasing its polynomial factor. So let's take a look at model 2. Right, so again, we're going to go back to our little example here, and we're going to expand polynomial to 3, right, here. Why? Because that's what we discussed as what model 3 is, W0, W1, W2 up to W3. So it's going up to W3. So we just change this expand polynomial to 3. Nothing else changes. So I'm going to close this. And let's run this again. Wow, okay. Model 3 is doing a much better job of generalizing. So model 3 is just right? It's actually giving us the representation that we want. Oh, sorry, I'm calling it model 3. This is model 2. Model 2 is just right. Okay. But again, remember the concept of generalization, right? Because what we want to achieve here with generalization is to make sure that it learns the general pattern. But as you can see, sometimes there's some outliers in this data set. How do we actually deal with these outliers? That's one question we might have in our minds, right? Like, how do we deal with this? And this will become important, like dealing with this kind of things. It will become important because if the model starts learning from these outliers, right, then that actually means what you call it, it will perform well on the training set, but on the test set it's not going to generalize well, right? This is kind of something you need to keep in mind. Having said that, let's look at model number 11, right? Let's look at model 11, model 3, sorry. I keep confusing it because of the number, but polynomial factor 11. As you can see, this model is a bit more worrisome. Why? Because it's starting to learn the exact patterns of the data, of the actual data set. It's not generalizing. It's really trying to match it almost perfectly. And this is a bit of a problem. This is a concept that is known as overfitting, right? So this is what we say, model 3, oh, wrong color. Model 3 is overfitting. So as you can see, model 3 is quite complicated. It goes up to a factor of 11. So based on this data set, what it's going to try to do, it's going to try to learn the exact patterns of this data set, right? Like that or whatever. This is an example of overfitting, when the best result actually would have been something like this, right? Which is, so this is model 2, this blue one is model 3, which is a problem, and the initial black one was model 1. So model 2 is the best model. Model 3 here is overfitting. It's learning way too much from this data set. The representation is too complex, right? And why is this a problem? Because when you go to the test set and say, what's the actual prediction for this point? The actual answer might be, the the prediction for this point. The actual answer from model 2, which will be here, which is more general, but model 3 is going to say it's this value here. So this is the prediction by model 2, and this is the prediction by model 3. Now model 3 is a problem, because model 3 used an outlier to make a prediction. But we shouldn't actually consider that, because this is an outlier. We shouldn't be having this in our model. The model should just find a general pattern, because an outlier will give us wrong predictions, right? Hence, this is why it's very important to find the right value of m. Should we use m is 1? Should we use m is 3? Should we use m is 11? Very complicated, too simple, just right. Just keep that in mind and you'll understand this quite well. So the thing is, again, you don't need to know the details of how we're computing w. You don't need to know the details of how to choose m just yet. Just know that when choosing m, these are the implications, right, that you could have, why it's actually important. And just know that we need to minimize the difference between target and predicted to be able to compute the w. So there are closed form ways of solving this. There are other methods such as gradient descent and stuff for finding the w's, and we're gonna go through these things later on. But for now, I just want to keep things simple so that you just understand on a high level what it is exactly that we're trying to achieve here. So having said that, let us actually move further with this whole concept of generalization and choosing m. So what we might realize is, okay, if you remember, our training set is the examples we're learning from. So again, in our training set, we would be given x1, x2, up to xn, and the targets t1, t2 for a supervised learning problem up to tn. And then in our test set, would be given x1, x2. These are different x's, by the way. Let me just put something here so that you know that this is something different. And then, but we don't have the corresponding targets. This is what we're trying to predict, right? So we can evaluate our algorithm, compute the the error on the training set. So we can compute the error here. We can also compute the error on the test set and actually see how it goes, right? So given this, so what we'll notice is, this is m, which is the polynomial model size and so forth. So here we say m can be 0, it can go all the way up to 11, up to some value. So m, like, as we make our model more complicated, right, it kind of like the error, this is the error, right? The error on our training set keeps going down, right? It will keep going down until it's perfect. This is for training. This is training error. But then we'll notice that on our test set, yes, it will go down. The tested error should probably almost always be higher than the training error. But after a certain point, this happens. and this is our test error. So what are we learning here? What we can actually infer from this is that, okay, as we make our model more complicated, that's good, because up to a certain point, um, our test error is minimized or whatever, right? And this will be just right. But when we reach areas like here, the area that you got here, of course the training error is low, but the test error is very high. So this is an example of overfitting. This is how you capture, this is how you check if your model overfitted. So you look at the training error, you compare it to the test error, you look at your models, and then you go like, at what point is the test error suddenly spiking up, right? This is where you say, no, this value of m is too high because my test error is now high. So the model started overfitting. So never use your training error to determine how good your model is doing. Always look at the test error. We're going to look at more complicated methods that are better at actually evaluating how a model is doing, such as validation, cross-validation, k-fold, and so on. But for now, this should be sufficient for you to get an idea of how you should choose the right value of m, right? So you need to be careful when it comes to such things. Like, that's the basic idea here. So having said that, another version, so we call this the error that we're computing, the sum of squared error. There's also another version of this error called the root mean squared error. So this I'm just introducing so that you're just familiar with it, which is equal to, so if you remember, we defined, where did we define it? This is our error, EW, that we wanted to minimize. This is a sum of squared errors. But now there's something known as the root mean squared error, which is the square root of 2 EW, right? E of W, and you know what E of W is. EW star, where W star is just like the optimal ways that we need to actually find, divided by n, where n is the number of sample points or number of dataset points. So this is called the root mean squared error. Why might we want to use this? Because by dividing by n, we can actually, so there's an advantage of dividing by n whereby we can compare different size datasets on the same scale. That's the actual inspiration for dividing by n. So if your dataset is of size 300 and another dataset is of size 20, you can just compare them on the same scale, like by using this error term. So this might be quite useful. And the other thing is, why are we taking the square root? But this just makes sure that the error term and is on the same scale as the target variable that we're actually computing the error on. So these are just little tricks and tricks that might actually give us a better interpretation of what the error actually is. So this is not, there's so many error functions we can use and so on, and we will discuss more as we go on. But for now, I hope that you got a general understanding of the importance in model selection, which is trying to find the perfect value of m, which we'll go into in detail later on. The importance of how do we actually compute this w, not how, but more like a high level view of the how, I should say. Like why it's important to find these values and so on, and what they actually mean, and how to avoid overfitting, how to check if our model is overfitting from a very simple perspective, and what is actually underfitting, and so on, and a few representations of the error function. So I hope this has been useful to you. Thank you for your time, and I'll see you in the next lecture when we are gonna start talking about probability. We'll start introducing Bayesian concepts, and this is where we're actually gonna start going more into the statistical statistics part of the statistical machine learning. So this will be an introduction to probability and so on, a quick overview so that you have an idea of what we're covering. So see you in the next lecture. Thank you.